Thank you. Good morning. So I'm Sylwin Pawlowski, as mentioned. I'm from Laboratory of Membrane Processes in Lisbon. We are around 40 people working on preparation of membranes and development of membrane processes. Well, I prepared this presentation 1 week ago, so I didn't know what is your background, so perhaps it's a little bit more complicated to explain everything. But basically, a membrane is a selective barrier which can be used to control the mass transfer, so the transport of different species between two different phases, so different liquids. And some of applications of the membranes, for example, we can control the mixing of river water and seawater in order to generate power. Another application of membranes is, for example, for water desalination. So basically by electrodialysis or by reverse osmosis, we can remove salts from the brackish water or from seawater and to obtain fresh water. We can use a target selective membranes for a specific ion. So for example, we are working a lot on lithium recovery from brines or from brackish waters in order to recover lithium. And another application is, for example, wastewater treatment. It's one of the most popular areas in the use of membranes, basically by, for example, by using a membrane bioreactor, we can remove the pollutants from the water to obtain potable water for use. And the membranes might have different structures. They can be symmetric, they can be asymmetric, they can have pores, they might be dense. So, basically the structure of the membrane and obviously the material of the membrane, they strongly influence the mass transfer through the membrane. So therefore the image analysis is so important for us in order to understand with what is the structure of the membrane, how the pores are connected, interconnected, what can be possible pathways for the transport of species through the membranes. So what we did, actually in this case, we used a monolith. So it's not a membrane, but it has similar properties to the membrane. And in this case, you can see that it has this hierarchical structure. So, and it's used basically for proteins purification. So what we did was to obtain X-ray tomography images of our monolith when we reconstructed its structure from those images, built the mesh, and after having the mesh, we performed CFD simulations by OpenFOAM in order to predict the flow patterns, tortuosity, and residence time distribution through our monolith. So this is the starting point from which we started to work. So this is the 3D reconstruction from the X-ray tomography images. The X-ray tomography images were actually done in Toulouse by Professor Martine Meireles. And what she gave us was the STL files with which we worked. So from these images, we cut two volumes. One volume was higher than the first one in order to check if we can simulate just a very small part of a column in order to predict the behavior of the entire column. And also we used the two different volumes basically to see if we are going to have similar results, or basically test the existence of finite size effects. So as I was saying, we performed CFD simulations. It was done already some years ago, so it was still version 5.0. But basically we solved it with Navier-Stokes equation, so we obtained the velocity and pressure fields, and then we simulated the trace injection through the column in order to obtain the residence time distribution curve. So here you can see some images of what we computed. So on the left you can see the streamlines through one of the volumes, and on the right you can see the several parameters which we computed. So the shear stress, velocity, pressure fields, and the concentration of a tracer through the monolith. And the shear stress is something extremely important for protein separations because basically they are shear sensitive. So above a certain shear stress, basically they denaturate. So it's very important to optimize the flow rate in order to achieve the best protein separation, the best protein purification before they denaturate. So from the streamlines, we calculated the tortuosity. So basically by knowing the length of the streamlines and by knowing the shortest distance between the beginning and the end of the streamlines, we computed the tortuosity values, and the obtained values were very similar to the experimental, analytical, and numerical known predictions. And here you can see the simulation of a tracer injection from the bottom to the top. We injected the tracer is going up, and it starts coming at the outlet. So it was a 30-day simulations on 3 processors, so it took quite a while to perform. And basically, from the average concentration of a tracer at the outlet, along the time we were able to obtain this residence time distribution curve, and we compared the CFD results with experimental results. And you can see that there is this very good agreement. What is a little bit different is that the CFD curves are a little bit narrower than the experimental curve, and basically it happens because obviously acquisition of the image has some limits in resolution. So the small parts of the monolith are not captured. So basically when we reconstruct the monolith, basically the channels are a little bit more open and wider. Therefore the dispersion in the CFD simulation is lower than the real experimental dispersion. Those CFD curves are a little bit narrower, so everything is as it was expected. We are also working a lot in our group on digital twins of membrane processes for CFD simulations. So, for example, on the left, you can see the real image of electrodialysis stack together with the spacers, together with the casket with mesh. And on the right, it's virtual reconstruction. So you can see here the reconstructed spacers, they are very, very similar. And basically, we performed CFD simulations. So on the left, you can see a channel with spacer. On the right, it's channel without spacer. So basically, spacers are very important for membrane processes in order to promote the uniform distribution of the fluid through the channel. And basically, CFD simulation, we are using them to optimize the shape and the dimensions of the spacers. And here on the right, you can see a comparison between CFD results and experimental results obtained in 4 different stacks for different flow rates. As you can see, the dots are the experimental results. The line is the CFD predictions, and you can see that we are obtaining some quite good agreement. So as I was saying, the channels, the shape of the channels for the membrane processes is very important. So what we also did was not to use just the flat membranes, because membranes are usually flat, but we did some corrugations on the surface of the membranes in order to promote a better mixing of the fluid inside the channels. So the pillar ones are the traditional non-corrugations. The chevron profile membrane is what we propose based on CFD simulations. And basically, we computed the mass transfer coefficient, we computed the pressure drop inside the channels with chevron simplified, and with pillar corrugations. And CFD simulations were suggesting that the chevrons are going to be the best one. And indeed, you can see here in the bottom that the experimental net power density, which we obtained by using chevron profiled membranes, was indeed the highest one among all compared results. So here's another example of a digital twin which we built. In this case, we are using flow electrodes what is interesting is that they are a non-Newtonian fluid. So in this case, they have this shear thin behavior. So basically, the viscosity decreases with the increase of the shear rate. And this was very important as in the beginning when we started to operate this technology. So on the left, you can see that with vertical serpentine channels, they clog it. They completely clog it. We have to stop the process because it was not working. Then we performed the CFD simulations in order to understand what was going on. And we had to do it because the flow electrodes are black. It's carbon suspension. So basically, you don't see anything. It's you see something dropping, but you cannot visually inspect that because all is black. So basically, you don't see anything. But by CFD simulation, we did simulation and we saw that the viscosity in these long channels increased to the values which basically suggest that they will clog. When using the horizontal serpentine channels, the viscosity is much lower, and basically this worked quite well. We also see from the streamlines that, for example, when using water, there is a mixing. This is called a dim flow. But when using the flow electrode, so on the right, there is no mixing. It flows, the viscosity is low, but there is no mixing between the layers of the flow electrode. So now we are working to improve this design. But meanwhile, we did a scale up of our process. So in order to predict how to keep the viscosity low, how to minimize the pressure drop, we tested different designs, different flow electrodes in order to predict at which regime we can work. And based on these CFD simulations, basically we did the scale up from a very small cell to a big prototype. And currently, this is the biggest prototype which exists in the world for flow capacity realization, and it was designed only based on CFD simulation or CFD inputs, and it works. So here's another example. It's something similar on what we saw on Monday. The last example on Monday, the one about the aorta. So here, what we were interested is how it's a hepatic vein with a device inside hepatic vein. So basically, this device is used to capture the excess of a chemotherapy drug from the system. So basically, what we wanted to see how this insertion of a device will affect the blood flow in the vein. So again, we performed CFD simulations, and basically we saw if the viscosity will keep low, if the pressure drop is high or not, how it will affect. We asked it then the doctors if it's suitable or not, and we also saw what is the distribution of the fluid through the device. So if all the surface of the device is being wetted by the blood, so in order to more efficiently remove the drugs from the system. And in the end, actually, we even 3D printed, so it's very, very small device. It's like 5 centimeters, and we printed it by using SLA 3D printer. So on the left, digital twin. On the right, the real 3D printed medical device. To finish, what is the main problem of membrane processes is fouling. Because when we treated water, they have organic compound, they have colloids, they have clay. So basically, the channels of membrane processes, they may clog. Also, the membranes, you can see here, for example, an example of absorption of humic compound, which are an organic compound on the surface of the membrane, which was in contact with river water. Also, the pores of the membranes may clog, so fouling is a big issue in the membrane process. And basically, here we are hoping that image analysis may help to solve the fouling problem, or at least to allow monitoring the fouling development. So far, what we are doing is to use the spectrophotometric method. So by 2D fluorescence spectroscopy, basically we acquired the spectra of the membrane surface in order to, you can see that they change a long time. As the membrane was getting fouled, the spectra also changed. So this is very complex information, because basically it's around 4,000 excitation emission pairs. So in order to extract the useful information, we are using principal component analysis. And when we are using PLAS modeling, which is multivariate statistical modeling, to predict the parameters of a membrane process based on PCs of the spectra and on operating variables. So to finish, basically, just to resume, we develop a lot of computational methods as a support for membrane-based technologies. We focus a lot on this 4 industrial revolutions, so on the use of digital twins. We also use 3D printers, so to print the medical device, but also print the flow electrode compartment, print the stacks. And I think there is a lot of questions now how to integrate all of this knowledge into a useful output. So we are interested in membrane process, we are interested in fouling. So basically, we can obtain a lot of information from simulations, from spectral analysis. I hope that image analysis can also help us, but there is also questions how to extract the information from all these sources. We are doing it by principal component analysis, but perhaps different methods can be used, and how to integrate all of this information, different information, into a single model in order to, in our case, predict membrane process performance. So thank you very much.